Welcome to our ME452 final presentation on the analysis and redesign of a mini gumball machine by Team 17.
Our production is a mini gumball machine for small gumballs or jelly beans. It is about 5 by 5 by 10 inches and holds up to 1.5 pounds of candy. Turning the knob activates the gear system to release the candy. Primary customers are businesses like arcades and restaurants, while secondary customers are families purchasing it for home use. The market value is around $1.2 billion. This diagram shows how the gumball machine dispenses candy from containing and guiding the gumballs to accepting coins, turning the knob, and opening the chute. The exploded view highlights key parts such as the cap, globe, gears, and base, showing how each connects and functions within the fully assembly.
This is our functional component mapping matrix. As you can see, it has all of the functives listed across the top, as well as all of the components listed along the side. It is important to note that all of the components have at least one function as illustrated by the X's in the table.
Moving on to the product family design, when taking a look at our primary and secondary customers, two functions change. One being the involvement of a coin, so that includes securing, accepting, routing, and depositing a coin, because when it comes to our secondary customers, the gumball machine will be more for entertainment and fun rather than for profit, so there's no need for a coin. And the second function changing includes containing gumballs, as in it should be easier to replenish and access the gumballs since it will be in a home and not unsupervised in a store. The modules that pertain to the function of the coin include the spider ring, coin mechanism release, and the coin mechanism front plate. And the modules pertaining to containing the gumballs include the cap and the globe.
The initial assembly analysis of the primary product variant, meant for businesses, showed a total time of 147.41 seconds and an efficiency of 32.56%. The two time-intensive steps identified were the baseplate and body attachment, which are of high functional importance given how they form the main structure and hold the coins, are also of high cost due to them being die-cast parts. The globe and retaining ring assembly, which secures candy and helps maintain candy freshness, is of moderate high importance but low to moderate cost. These steps were chosen for redesign because they dominate assembly time and represent high leverage opportunities. Small geometry or fastening changes can reduce handling and insertion time without compromising part function. The results after the changes were the reduction of the total time for assembly by 17.43 seconds and an efficiency increase of 4.37%. As the changes were not invasive, the manufacturing cost should see minimal impact. The exact calculations were added as part of the appendix at the end of the slides. The baseplate initially lacked orientation features, so it had to be held in place to keep the screw hole aligned with the one in the body. To fix this, we added an asymmetric orientation feature, following DfA 7, which lets the plate self-align and reduces handling time. The original screw was an M4 8mm long fastener, different from the other 6mm screws used. Standardizing all screws to be 6mm long, as per DfA 5, reduces fastener variety and simplifies the assembly. Finally, the central cone of the baseplate could cause parts to stick when stacked. We added an anti-nest feature according to DfA 8 to prevent sticking and make part retrieval faster and more reliable. For the globe and spider retaining ring stacking, minimal changes with big impact were implemented. The globe was too light to stay secure on the gasket by itself, so it had to be held while the rest of the parts were placed. To fix this, we increased the height of the body following DfA 10, so the globe can be inserted easily without holding it to prevent from tipping over. The spider ring had very little clearance around the inner rod, making insertion take longer than needed. We added a leading feature, also per DfA 10, to guide the spider ring and simplify placement. Finally, the spider retainer ring was originally held in place with a hex nut and the cap with a screw plug. But the hex nut wasn't necessary due to the screw plug being able to hold down the spider retainer ring and the cap on its own. We eliminated the hex nut fastener, according to DfA 2, which reduces handling time. All these changes allow for a more efficient manual assembly.
Next, we completed our design for automated assembly analysis, focusing on the coin mechanism subassembly, which contains the knob, front plate, back plate, gear, knob slot, and release. These components are justified as they have a high importance and combination of high and low manufacturing cost, as shown in the quad chart. The pre-automated assembly analysis has a total handling and insertion cost of $88.38. After redesigning the parts with DfA in mind, the total handling and insertion cost was reduced by approximately $20 to a total of $69.30. This was based upon the assumption that the feed rate was 1 part per minute according to expected production. Here we see the before and after automated assembly analysis. We first added a small extrusion on the gear to allow for smoother placement of the screw, which adheres to DfA 10. This change is shown in green. The next change, shown in red, consisted of removing 2 fastener locations. This fulfills DfA 2. The final change shown in blue relates to DfA 11 as it provides locating features. In the new design, we extended the boss on the front plate to allow for the back plate to be guided. It is important to note that these changes did not alter the functionality of the gumball machine but improved the overall assembly process.
One of the most important parts that we need to consider that we altered previously is the spider retaining ring. In order to select the process in which to manufacture, we compared it to machining, sheet metal working, injection molding, and die casting. We determined that the most critical dimension was going to be the inner radius of the large hole, just because it needs to contain the gumballs, so it can't be too big or too small, because it needs to allow the gumballs to get through, but it also can't be too big that they will slip out of there when inside. That led us to a tolerance of plus or minus 0.005 inches based on being a generally sized internal part with nothing super special about it. And all of the criterion that passed were for injection molding.
For the plastic component, DfM Pro didn't flag manufacturability issues, so we used the injection molding lecture guidelines to review the original design. We noted 3 concerns: slightly excessive wall thickness, minimal draft, and sharp internal corners, all of which increased material usage and reduced mold efficiency. The initial cost per part was around 61 cents. After applying DfM principles, we reduced wall thickness, added proper draft angles, and removed sharp corners to improve flow and ejection without affecting functionality. These updates lowered the cost to around 58 cents, giving us about a 2-cent reduction per plastic part.
Similar to the spider retaining ring, we also did process selection on the coin mechanism front plate, whose most critical dimension is 0.1 inches with a tolerance of plus or minus 0.03 inches, which is based on being a mainly cosmetic part. We also did the criterion compared against the 4 different types of manufacturing processes, and die casting was selected because it passed all of the criterion.
For metal die cast component, DfM Pro again did not highlight issues, so we relied on the die casting lecture slides to evaluate the pre-DfM design. The lecture identifies 3 key risk areas that we also saw here: non-uniform wall thickness, sharp interior edges, and insufficient draft. These conditions increase solidification defects into aware, even though DfM Pro did not flag them automatically. The initial die casting tool was $1.92 per part, which served as the baseline. Following the recommendations from the die casting lecture slides, we updated the design by standardizing the wall thickness, adding correct draft angles, and removing sharp corners to improve flow and reduce die stress. These lecture-based improvements simplified the tooling and slightly reduced the material volume. After redesigning the part cost, dropping from $1.92 to $1.85, resulting in about 8 cents reduction per cost.
To enhance our product, we will offer a candy refill shopping and subscription service available over website or app. The gumball machine connects to Wi-Fi and is registered through the customer's account. Machines detect how often the knob is turned to determine candy levels in the globe. Customers can either subscribe to periodic candy refills or get notified when it's time to purchase a refill. The shopping software will also include various candies, all perfectly portioned to fit the globe. Customers can take surveys to determine initial candy preferences and can continuously fill them to share opinions on new candy shipments. Commercial customers can take advantage of analytics services to determine candy preferences of their customers by seeing how often a customer purchases candy over the period of time after a new candy is added to the machine. Overall, this enhancement improves customer experience and environmental impact by offering preference-based portion-filled packs that reduce food waste and increase convenience. Commercial customers can see boosts in business from new exciting candy refills. Both types of customers will likely see lower costs due to bulk candy purchases being cheaper for us to distribute and fresh packages for them to receive. In conclusion, we reached our goals of redesigning this product with DfM and DFA in mind. Part standardization and feature additions made it possible for us to cut manual assembly time by 17.43 seconds. Removing unnecessary fasteners and slightly changing part geometry in the coin mechanism allowed us to reduce automated assembly costs by $19.08. Creating reduced uniform thicknesses, adding draft angles, and avoiding sharp corners made it possible for us to reduce part cost of the spider retaining ring by 2 cents and the coin mechanism front plate by 8 cents. Overall, our redesign is more lightweight, easier to refill, and has made it harder for customers or kids to take the candy out of the globe. While we have reduced part count, some part designs have become more individually complicated. If we were to take a new approach, we would redesign for specific use cases rather than generic residential or commercial settings. We would also reduce and redesign parts for multiple functions rather than modify existing parts for ease of assembly, not increase utility. Thank you for taking the time to listen to our presentation.